Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on January 15, 2026, just yesterday. It introduces a new framework called SocioReasoner that combines satellite imagery with digital maps to successfully segment socially defined areas, like schools and parks, which are notoriously difficult for standard vision models to identify. The paper is titled Urban Socio-Semantic Segmentation with Vision Language Reasoning. And as we'll see later, the results demonstrate strong zero-shot generalization across entirely new geographic regions. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core difference between traditional segmentation and this new socio-semantic approach. On the left in Panel A, standard models focus on physical objects, like labeling a generic building based purely on visual cues. In contrast, Panel B shows the new socio-seg task, which uses map data to identify complex social entities, organizing them into a hierarchy from specific names to broad functions like sport and cultural. The bottom row then compares the workflows. Unlike the single-stage method in Panel C, the SocioReasoner in Panel D uses a render and refine loop, iteratively updating the result for better precision. While Figure 2 details the SocioReasoner framework itself, the top half illustrates the two-stage inference process. Initially, the vision language model predicts a bounding box for a target, like a school, which generates a coarse mask. Then, in the refinement step, this mask is rendered back onto the input, allowing the model to critique its own work and add specific point prompts for a final, sharper segmentation. To make this work, the bottom section shows their training setup using group relative policy optimization. The system generates multiple reasoning chains and evaluates them using the reward functions listed on the right, which prioritize valid formatting, high accuracy, and concise reasoning. Alright, Figure 3 presents the visual evidence that this framework actually delivers. The large top panel compares predictions across different hierarchical levels, like identifying Jinanzu by name, or classifying an express delivery station. If you look at the columns on the far right, you can see that the second stage of SocioReasoner produces masks that align much more tightly with the ground truth than the single-stage baselines. Then, in the bottom left, we get a peek under the hood at the reasoning process itself. Here, the model explicitly outputs a think token and a text chain, first locating the zoo on the map, and then refining the boundary based on visual features like buildings and greenery. So while Figure 3 showed qualitative examples, Table 1 quantifies the performance across the entire test set. The columns here split the results by hierarchy, starting with specific socio names on the left, then broader classes, and finally functional zones. We see comparison groups for standard vision models like UNet and specialized remote sensing baselines. Across the board, the proposed framework, labeled as Ours in the bottom row, consistently takes the lead. In the full dataset summary on the far right, it reaches an F1 score of nearly 60, clearly outpacing the competition. Okay, comparisons on the standard test set are one thing, but Table 4 asks a tougher question. Does the model generalize to completely new cities? The results are split into three scenarios. In-domain data on the left, different map styles in the middle, and the hardest challenge on the right, labeled Out-of-Domain New Region. This last group includes unseen cities like Tokyo and Nairobi. If you look at the bottom row, Hours with RL, you can see the impact of reinforcement learning. While the supervised version drops to an F1 score of about 31 on new regions, the RL-trained model holds steady at nearly 43, proving it is much more robust to unfamiliar geography. Well, Figure 6 provides a detailed breakdown of the socio-seg dataset structure. The pie chart in Panel A shows that the data is fairly balanced across the three hierarchy levels, with the largest share, about 43%, devoted to socio-classes. The bar charts in Panels B and D then list the counts for these categories, covering everything from broad functions like commercial services to granular labels like shopping malls. Finally, Panel E at the bottom presents actual training triplets, pairing satellite images and maps with precise masks for entities like the Beijing Planetarium. Wrapping up, two takeaways stand out. First, combining satellite images with map data enables models to understand social contexts, not just physical shapes. Second, the reinforcement learning-driven refinement loop is critical for generalizing to new cities. This approach marks a significant step forward for automated urban planning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.